So the topic of this lesson is the dimension of row A and column A. I want to remind you of the definition and a few theorems that we've already seen. So first of all, what is row A? Let's start with row A. So A is a given matrix, and row A is what we call the row space of the matrix A. And this is just all possible linear combinations of the rows of A. Okay, so the subspace spanned by the rows of A. Okay, are the words compiling? Are the terms already clear? Okay, so let's write it. Linear combinations of rows of A. Okay? And here are a few theorems that we've already seen. We didn't prove all of them. Some are not that easy. But here are the facts. So the first one was, if A and B are two row equivalent matrices, so if we take two matrices that are row equivalent, meaning that we can pass from one to the other using elementary row operations, then the rows span the same subspace. So row of A equals row of B. We even mentioned that this is an if and only if statement, although this is the direction we discussed in more detail. Okay. The second theorem that we had was if A and B are row equivalent, then the rows of A are linearly dependent if and only if the rows of B are linearly dependent. So the property of being dependent or independent for the rows is preserved under these row operations. Okay? So implies that the rows of A are linearly dependent if and only if the rows of B are linearly dependent. Okay? And the third property was that the non-zero rows of a matrix in echelon form are always linearly independent. Okay, remember that? The non-zero rows of a matrix in echelon form, do you understand why I'm doing this, are linearly independent. Okay, so the non-zero rows of a matrix in echelon form are linearly independent. So in fact, it was the combination of 2 and 3 that was the justification, the idea behind the method that we derived in order to decide if two sets of vectors, or if a set of vectors is linearly independent or not. Okay, we set the vectors, and now we can even say it a bit more formally. We took the coefficient vectors of those vectors, whether it was matrices or polynomials, we straightened them out as rows of a matrix. Okay, that's simply taking their coefficient vectors, and then we did row operations until we reached the echelon form, and saw if we had rows of zeros or not. If we didn't have that, they were linearly independent to start with, right? Because of this. And then that means that the original one was before the row operations. So if B is the echelon form, then A before the row operations was also, the rows were also linearly independent. Good? Okay, so these ideas we discussed in a lot of details and showed many examples. I'm just now kind of referring back to them and trying to put all these in context. Okay, good? Okay, so what I want to do now is discuss what is the dimension of the row space of A. Of course, what the rows of A span, okay, the linear combinations of the rows of A, is not all of them are necessarily linearly independent. So it's not necessarily a basis, right? There could be extra rows. If you take the same row 17 times, of course, the span will not change. Okay, so what is the dimension of this space? The space spanned by the rows. Okay, and that's going to be the theorem, which I am going to prove. And it says the following. So here's a very short phrasing of a theorem. The dimension of a row space of a matrix is in fact nothing else but the rank of the matrix. Okay? The rank of the matrix we defined as the number of non-zero rows in the echelon form. Okay? So the dimension of the row space is in fact the rank. Okay? We will prove this in a second, but do you agree that we could have defined the rank of a matrix? Once we prove this, it would mean that we could have defined the rank of a matrix to be the dimension of the row space. The reason we didn't do it that way is because we discussed the rank and its role in solving equations and so on much before we mentioned vector spaces and in particular bases and dimensions and all these properties that we're going to need. So we defined the rank as something very tangible. Do the row operations and look at the number of non-zero rows. But in fact, this is a very standard definition, and now I want to show you that they coincide. Okay? So here's the proof. And of course, the proof is going to be based on these three statements that we had on the previous board. So let A be a matrix. Let's do row operations until we reach its echelon form, some echelon form. So let B be a matrix in echelon form, which corresponds to A, which is row equivalent to A. Okay? How many non-zero rows are there in B?
The rank of A.
Exactly. There are, very good, there are precisely R of A non-zero rows in B. In B. Why? Because that was the definition of R of A. Okay, the definition was go to the echelon form, count how many non-zero rows you have. That is what we call the rank of A. And it's independent of which echelon form you chose, and therefore it's well defined. Okay, so do you agree? So this property, we mentioned this before, the property of the rank of a matrix cannot be seen from the matrix itself. It can only be seen after you do the row operations and reach the echelon form. Okay, it could be read off B rather than off A itself. Okay, good. So there are R of A non-zero rows in B. So let me add by definition of R of A. And these non-zero rows are linearly independent. Why is that? How do I know that the non-zero rows are linearly independent?
You can add another row.
Shorter answer.
It's echelon form. That's what it means.
So,
You can't make more zero rows.
I want a very precise answer, which
None of
is
them-
made up of one word.
It's not special.
One word.
This earlier.
You're saying more than one word. Stop talking, think. One word. I'm challenging you. It's not even a word. Do you agree? That was precisely theorem 3 on the previous board. Let's look at it. The non-zero rows of a matrix in echelon form are linearly independent. Okay? This is the idea of mathematics, right? You make a definition, you prove theorems. Of course, in this class, we're not proving everything, because we're just kind of giving the story, proving some things. But once you have a theorem, that's it, it's yours, it's a fact. Okay? So that's it. We don't need to go into the justifications of why this is true or not, whether intuitive or formal. Okay? It's a theorem, it's ours. Good? So the non-zero rows of B is an echelon form, are linearly independent. That's precisely what I wrote here. Good? Okay. Now, these rows, these non-zero rows, these rows span row of B. Row of B is the space spanned by all the rows of B. But the zero rows contribute nothing to the span, right? So the non-zero rows already span row of B. Okay? So the non-zero rows span row of B and they're linearly independent, right? So in fact, these non-zero rows are a basis for row of B, right? Therefore, the non-zero rows of B are a basis for this space row of B. Do you agree? And we just said that there are R of A many of them, right? So the dimension of row of B is R of A. Do you agree to that? Because this is a basis. There are R of A elements in a basis for row of B. Therefore, the dimension of row of B is R of A. Okay? And now, if we go back to the previous board again, A and B are row equivalent. B is the echelon form corresponding to A. By theorem 1, row of A and row of B are the same. So the dimension of row of A equals the dimension of row of B, which we just showed is R of A. Okay? So let me write that. Are a basis for row of B, which equals row of A by 1. Do you agree? And the conclusion is, I'm sorry for writing at the bottom of the board, but this is really the end, the dimension of row of A equals the dimension of row of B equals R of A. Good? Everybody? Follow the details? Okay. So, R of A, which was originally defined as the non-zero rows in the echelon form derived from A by row operations, is in fact the dimension of the row space of A. Okay. Remark, just re-saying things that we already know, that's what we use in order to find what is row of A, what is a basis for row of A, for example. So this is precisely how we find, this is exactly the method to find a basis for rho of A. Okay, so what do I mean? When we see the rows of A, we don't know that they're a basis because we don't know if they're linearly independent or not. So we do the row operations until we reach B, and then the rows of B are a basis for the row space of A. Okay, so for example, if A equals our favorite matrix 1, 2, 3, 4, 2, negative 1, 1, 0, 3, negative 2, 1, 2, if this is A, we've seen several times that by row operations, elementary row operations, what we get is 1, 0, 1, 0, 0, 1, 1, 0, and 0, 0, 0, 1. So this is B. This is an echelon form, right? So the rows, the non-zero rows, and in this example, all of them are non-zero rows. These non-zero rows are a basis for the row space of A. So example. So call this B. B is an echelon form. So what we get is that 1, 0, 1, 0, this vector, and then 0, 1, 1, 0, and then 0, 0, 0, 1 is a basis for, it's obviously a basis for row of B, but the whole idea is that it's in fact a basis for row of A. Clear? By the way, can you see on the board a different basis for row of A? In this example.
Sure. I mean, we can perform more operations and it will change.
Okay, you can do reach a different echelon form. For example, if you multiply the first row by 2, it will still be echelon form, right? It won't be the canonical form, but it would still be echelon form. That's true. But there's even something more you can say.
Maybe if you switch the zeros in the ones, but I'm not sure about it.
No. Look at the rows of A. Okay? Once we know that all 3 rows in B are linearly independent, okay, that means that the dimension of row of A is 3. We found the basis with 3 elements, okay? These are, the rows of A itself are 3 vectors that span row of A, of course, okay? So they have to be linearly independent. And in fact, these 3 rows in this example are themselves a basis for row of A, okay? So note that in this example, the rows of A itself are another basis for row of A. Okay? Because the dimension is 3, they're a spanning set of dimension 3, therefore they're linearly independent by theorems that we had last time regarding the number of elements in a basis. Okay? Okay. What I should also remark in following this remark is that suppose we had 3 matrices, and we did this, we discussed this, for example, the matrix 1, 2, 3, 4, a 2 by 2 matrix, and the matrix 2, negative 1, 1, 0, and the matrix 3, negative 2, 1, 2, the way to find the basis for the set of matrices generated, spanned by those 3, would be precisely this. We would set them as rows in a vector, in a matrix, right? That would be taking their coefficient vectors, Okay? Performing the exact same method, concluding that the three, or maybe two of them, right? In general, why aren't the rows of A always a basis? Because sometimes after row operations, there could be a zero row. And then only two of them, or only one of them, or if there are 17, only 13 of the 17 can be a basis. Okay, and then to see from the original one which ones were the basis, that could be difficult. Okay? Okay, so let's do just one more example. Suppose W is the span of, here are four 2x2 matrices. Sorry, three 2x2 matrices. We may have had this specific example before. I'm recycling examples. Recycling is a good thing, right? It's important, right? So the way to find the basis for W, which is a subspace of 2x2 matrices over R, okay, and a priori by seeing them we do not know if they're if W, what the dimension of W is, right? It could be 3, it could be 2, it can't be 1, because we can see that if it were 1, then all of these should have been scalar multiples of this one, and that's not the situation. So just by looking at it, we know it's either 2 or 3. Those are the only two possibilities. Do you agree? Okay, it can't be 4 because there are only 3 of them. It can't be 1 because they're not all scalar multiples of the same one. So it's either 2 or 3. So what we do is we write their coefficient vectors with respect to the standard basis, which is another way of saying arrange the entries as rows of a big matrix. Is it clear that what just happened here, the transition from this to this, is in fact taking the coefficient vectors, writing them as row vectors in a matrix? Coefficient vectors with respect to the standard basis. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 0, 0, 1. Good? That was way too fast even for me. Good? Okay. Row operations. Echelon form. You can verify that what I did is correct. Turns out that the dimension is 2. 2 vectors are enough to span the rows of B. So let's call this A. Let's call this B. B is an echelon form. 2 rows are sufficient to span the rows of B, the row space of B. These are linearly independent because it's an echelon form. You can say it because one is not a multiple of the other. Okay? So the dimension of the row space of B, which is the same as the row space of A, because they're 2 matrices which were row equivalent, is 2. Okay? And now, without telling you what are the row operations that I did, you don't know if maybe this one and this one form a basis, but if we throw out this one, it wouldn't. Okay, so it's right here. It's easy because it's but if there are 15 of them, it would not be trivial to say which ones we need. But we can just take these, right? The span of these rows is precisely the span of all these rows. Okay, so the set 1, 2, 3, 4. We don't need the commas, right? We wrote them like this. 1, 2, 3, 4, and 0, -2, -3, 1 is a basis for row of B, and therefore row of A. And therefore, if I take the matrix, the 2x2 matrix, for which this is the coefficient vector, these are linearly independent if and only if the corresponding matrices are linearly independent, right? That was what we talked about last time. So these 2 matrices, this is a basis for W. Clear? Okay, so there's a bunch of ideas behind this. There's a kind of wrapping together all these ideas, but that's what it boils down to. Okay? If we want to find a basis for a given subspace, for a given space spanned by something, or maybe given as some restrictions, we saw many examples. We take the coefficient vectors, which is a different way of saying straighten them out as rows of a bigger matrix. Go to the echelon form, take the non-zero rows of that, and transform them back to your original vector space. Good? Okay. So let's talk now about the columns of A. So all of this discussion was related to rows. Now let's talk about the column space of a matrix. And I want to write first the definition, and I'm not going to erase everything purposely. Okay, I want to write it on this and tell me if you agree. So the column space of A, or col of A, was defined to be the column space. Column space of the matrix A, which is just all the linear combinations of columns. Of A. Do you agree to that? Okay. Now, do these theorems hold for col of A? Answer, well, they're not theorems about col of A, they're theorems about rows. Rephrasing of the question. Suppose I changed here to column, and here to column, and here to col of A, and col of B, and columns, and columns, and columns, and so on. Would these theorems hold? And the answer is yes. Do I need to reprove them again to go through the entire process? The answer is no. And the reason is that the columns of A, okay, suppose you have a matrix A, the columns are the rows of the transpose matrix. For the transpose matrix, we know these theorems about the rows, so for the original matrix, we have the corresponding results about the columns. Do you agree? Okay. So I want to erase this. I don't want to replace in each and every one of them the word column with the word row. You can do that if you want and spell these results out. But there's a reason why we've said so many things about rows, about the row space, and didn't mention too much the column space. We didn't have these theorems, okay? And the reason is that the row space was directly related to systems of equations. And that's why we always discuss row operations. We never did column operations, ever. Do you agree? So our motivation for defining the row space and studying it, and our applications of the row space and doing row operations, was systems of equations. And the column space is not. If you take the coefficient matrix and do column operations, you're messing up the system of equations completely. Okay, changing the columns of the coefficient matrix in a system of equations is changing the systems of equations. Different solutions, different everything. Really messing it up. Okay, so I want to emphasize that before I do anything further. The reason for which we were interested mostly in row operations and in row of A is the relation to systems of equations. Okay? So this is something I emphasized before and I'm emphasizing again. You cannot do column operations when you're looking at a coefficient matrix of a system of equations. That's false. Okay? It gives you a different system. Okay? We did mention column of A though. I don't know if you remember, because there was a relation between, even in relation to systems of equations, there was a relation. We could write the system not as AX equals B, but taking the columns of A and writing their linear combination with the x's being the coefficients. Do you remember we did that? And that's where column of A showed up. Okay? But that's not the direction that I want to discuss now. So this is the first remark. And the second remark is theorems 1, 2, and 3 have column analogs. Okay? They have analogs. You can phrase them for the column space, and proving them would just be transposing, doing the how do I show you transpose? Here's how I show you transpose. Here are the rows of A, transposing the proofs. Zhut, zhut. Okay? That's the idea. You don't need to go into the details of all the proofs again. But what we didn't define is what is the rank of A in terms of columns, right? When we defined the rank of A was the number of non-zero rows in the echelon form. If we want to define the rank by columns, if such a thing were to be defined, then it would have to be do column operations, reach the column echelon form, which is not the same as the row echelon form. It would not look like this, but rather, well, like this again, but by columns. Okay, reach the column echelon form and count how many non-zero columns you have in the column echelon form after you did column operations. Okay? But the point is that there's a better way to define the rank by columns. The rank by columns of a matrix A would just be the regular rank by rows of the transpose matrix. Do you agree? Okay. So let's write all that. I hope I'm not confusing you too much. So let's start by saying, note that the column space of A itself is precisely the row space of A transpose. Right? The linear combinations of the columns are precisely the linear combinations of the rows of the transpose. Okay? Moreover, the rank of A transpose, which is the rank of A transpose by rows, the regular good old rank. I'm not going to use a different notation for the same notation for two different things, but not the rank of A. The rank of A transpose is the rank of A by columns, which I'm not going to define. I'm just going to say it's this. So the rank of A transpose is the number of non-zero columns in the column echelon form of A itself. Okay? So if you take A and do column operations and reach column echelon form and count how many non-zero rows you have, that would give you the same number as taking A transpose and doing what we're used to, working on rows. And that's this number. Good? Okay. So if this is clear, this means that there are in fact two numbers involved. One is the rank of A itself, which is a statement about rows. And the rows of a matrix could be very different than than the columns of a matrix. You could have a matrix which is 3 by 18,000. Okay, it could have 3 rows and 18,000 columns. Okay, so a priori, the number rank of A, which is counting how many non-zero rows you have in the echelon form, and rank of A transpose, which is counting how many non-zero columns you have in the column echelon form, a priori they should be completely different numbers. Okay? And the theorem, which may look in a sense surprising, is that they're the same. The rank of A always equals the rank of A transpose. Okay? So, or in particular, the rank by rows is the same as the rank by columns. Maybe I'll even write that. Stated differently, the rank by rows equals the rank by columns. Okay, so I'm going to put this in quote marks, because by the rank by rows I mean good old R of A, and the rank by columns we never really defined, but we just said that in fact it's R of A transpose. It's this number. This is the rank by columns. Okay, the number of non-zero columns in the column echelon form. Okay, good? Okay. Now the proof of this theorem is in fact long, very technical, and this is again a theorem that I'm not going to show you. I wish I had time to show you all the theorems. Okay, that's what we do in the mathematicians version of this first algebra course. We actually prove all these, and in fact, the most intriguing ones are things like this, which look very surprising at first glance. And how would one prove such a theorem? And this is not an exercise, okay? So it's not something I would tell you go and try proving it on your own. It's not. There's nothing really deep going on there, but it requires some being familiar enough with the ingredients and the ideas to carry on a proof like this in full details. Okay, and we just don't have the time to go through everything. Some of the theorems are big mysteries. You can of course find them in references in Wikipedia or a good book, which is always a good companion for any course. I'm saying this seriously. Okay, it's a good idea to, if you're on top of things and if you feel good, go and take a look. See if you can read through the proof and understand it, and it's very valuable. Okay. Okay, so let's conclude some stuff from this theorem, starting with an example. It's going to be kind of a stupid example, in fact, but nevertheless, I want to show it. So, but before that, maybe let's write this corollary. What did we say? It's a double L? Is that what we agreed on?
We don't have the spelling man today.
Yeah, the spelling guy is not here. Okay, corollary. Was it a double L or a double R? Wow. Okay, this is embarrassing. The dimension of rho of A equals the dimension of column of A. This follows from the statement that the rank of A is the same as the rank of the transpose. Why is that true? Let's prove the corollary based on the theorem. So this is a straightforward proof. So what is the dimension of the column space of A? So we observed and we agreed that the column space of A is the same as the row space of the transpose matrix. So this is the same as the dimension of the row space of A transpose. Do you agree? Okay. The column space of A, what's spanned by the columns, is precisely what's spanned by the rows of the transpose. Good? So their dimensions are the same. Now, for the dimension of a row space, we know it's precisely the rank of the matrix. So this equals the rank of A transpose. By the theorem, this is the same as the rank of A. And by the theorem that we had previously, that we proved about, 30 minutes ago, this is the same as the dimension of row of A. Good? So this proves the corollary based on the theorem. Here's the theorem. This is where we used the theorem no, sorry, not here. Here is where we used the theorem. Good? Everybody? Okay. And here's the example. So suppose you have a matrix that looks like this. 1, 0, I'm just picking numbers. I don't know why I'm copying the ones I have here. You can pick any numbers that you want. 0, 3, 1, 4, and root 2. So this is a 5 by 2 matrix. What is the rank? It should be 2, and in fact, it is 2. Okay, so one way of doing it, you have 5 rows, you can start doing row operations and seeing that in fact only 2 remain in the echelon form, non-zero. Okay, that is a pretty long way to solve this. A shorter way to solve this would be, hey, let's look at the rank by columns. It has 2 columns. They're linearly independent because one is not a multiple of the other. That's it. That's it, we're done. The rank is 2. Because the rank of A transpose is 2, and that's the same as the rank of A. Good? So is this clear? Is it clear? And of course, when you have a matrix like this wouldn't be hard either way, but if you have a matrix with many, many rows and many columns, or sorry, the other way around, many columns, but many rows, you'd rather do the operations on the columns or take the transpose and do your good old row operations just so as not to be confused. Okay? Okay, so that's the example. I guess we can wrap this discussion here. So the rows of A and the columns of A, these spaces, row of A and column of A, in fact share a dimension. The dimension is just the rank of A, okay? And finding it is, by the theory that we just stated, finding it can be done either by means of row operations or by means of row operations on the transpose, or another way to say it is column operations. Just one big word of caution, which I'm saying for the I don't know how many time, but still I'm going to say it again. Beware, when you're taking a system of equations, if what you're doing is the augmented matrix of the system of equations, okay, or the coefficient matrix of the system of equations, only row operations. Column operations on a coefficient matrix of a system of equations is changing the system. The solutions you get are no longer related to the original system. Okay, big word of caution. Okay, so let's stop this one here.